Hi everyone and welcome to my YouTube channel. So the Maths and Science Top Dogs. So in today's video we're going to do a grade 12 stuff. So we're going to cover some past papers. In this one is going to be physical science, specifically November 2017. Alright, so I'm just going to cover the mechanics part. So meaning I'm going to do all the questions that are under mechanics. So if you haven't subscribed to this YouTube channel, please hit the subscribe button there and also share and hit the like button if you like the content. Okay, so specifically in this video we're going to do question 1 and we're going to do the mechanics question in question 1, and then after that we're going to go to question 2, do the mechanics question 3 mechanics questions, and so on. Okay, so we're going to cover the multiple choice first, then let's get started. The first question says that the acceleration due to gravity on Earth is greater than that on the moon. So we have our G on Earth is greater than G on the moon. So I try to get some pictures here. So this is the moon with an astronaut on it, and then this is Earth with an astronaut on Earth. Alright, so the mass of astronaut here on the moon is the same as the mass of astronaut here on the Earth, but the gravitational acceleration here on the Earth is not the same as the one here on the moon, as we are told, and we know that weight is given by the mass of this person multiplied by the gravitational acceleration here. So meaning that the weight of this guy is not going to be the same here, it's not going to be the same as his weight here. Alright, so let's move on. The first question says, which of the following statements is correct? So the weight of an object on Earth is the same as that on the moon. I just showed you an example here with this guy. So this guy here on moon is not going to have the same weight as on Earth, so this is wrong. And the second one says that the mass of an object on Earth is the same as that on the moon, so this is correct. The reason it's correct is because this guy here is still him, it didn't change anything, nothing changed, it's still the guy, so his mass is still the same wherever he goes. Like even if he's on Jupiter, on Mars, his mass is going to be the same everywhere. So here this question is correct, so let's mark that as a correct answer. Okay, so now we mark that as a correct answer, then we can move on. Okay, so C says the mass of an object on Earth is greater than that on the moon, so that's false. And D says that the weight of an object on Earth is less than that on the moon, that's false also. Then let's move on to question 2. Question 2 says that the first diagram below shows the forces acting on the box. So you have the box here and you have a normal force pointing upwards, you have a weight pointing downwards, and then here you have a force F acting at an angle. So the easy way to do this is just to decompose this force into two components, so that you have a force pointing in the same direction. So this, if it's decomposed, is going to have a vertical force which points the same direction as a normal, and one horizontal force which point to the right. So we are just going to omit that one that's pointing to the right because we are interested in the vertical forces. So it says, the question says which one of the following equations for the magnitude of normal force is correct. So we're looking for normal force. So as I said, we're just going to redraw the first diagram with this force decomposed. Okay, so here we got two forces pointing upwards and got one force pointing downwards. So since this object is moving horizontally, it's not moving in any vertical motion, then we consider the forces that are balanced, are in equilibrium, the vertical forces that are in equilibrium state, meaning that the two forces that are going upwards, this one and that one, when we add them, the mass give us this one that's going downwards. For these two to be balanced, imagine if your friend is pulling in opposite direction and you don't want your friend to to overcome you. So that means you're going to call your other friend to come and push with Fy, so that you two guys balance this one beast here. So this beast is going downwards, so in order for him to be balanced, we need two people here to pull in the opposite direction. So that's the idea behind this thing. So in order for this object to stay horizontal, not moving up and down, we need another force here that's going to add to the normal, so that two forces uh, are going to balance the weight. All right, so N plus Fy, which is this N plus Fy, it's going to give you weight, meaning that these two forces must be equal to this one force. Okay, so if we're making Fy the subject, or not making it the subject, if we are going back and finding the Fy, magnitude of Fy, so if you decompose this, that means this is going to be in opposite side. So you know guys, from the trigonometry, that the opposite over hypotenuse is equal to the sine of theta. So hypotenuse, our hypotenuse was F here, so here it's clear that this was Fy over F is equal to sine theta, and then we multiply both sides by F. That's why we have Fy now, it's F sine of theta. All right, so let's move on. And then now we are looking for the normal force. So you can see here that if we're making the normal force the subject, is going to be weight minus Fy. So if it's weight minus Fy, that means it's going to be weight minus this. All right, so A says that normal must be weight plus F cos theta. That's wrong according to our equation here. So the second one says that the normal force must be weight plus F sin theta. According to this, it's wrong. Weight must be normal force must be weight minus F cos theta. That's wrong also. And then the last one says that a normal force must be weight minus F sin theta. So according to this, is right. Therefore, this is our correct answer. So let's tick that, guys. Okay, so let's move on to the next question. 1.3 says that the stone is projected vertically upwards from the top of the building at a speed of v meter per second. The position time graph below represents the motion of the stone. Ignore the effects of air resistance, meaning that here we're dealing with a free fall. Okay, so I try to get some pictures that's going to help you understand this better. So let's take a look at this diagram first, the one that we're given. Okay, so here we got this first, we got this. So this is the position time graph that they told us about. Okay, so this is a y position, and then here's where the stone was leaving, and then like going up, and then at certain point it turns and then goes down. So take note that the velocity is going to be given by the slope of this position versus time graph. All right, so here, if you have been in Johannesburg CBD, probably you know this building. This is a Transnet building. It's one of those tall buildings in there. Okay, so imagine that you're standing up there and then you throw something downwards. So as that thing is moving to the ground, it's going to move in this path. It's like you throw that thing upwards, and then after that, at certain points, it's going to turn and fall back to the ground, unless if you throw it with enough velocity to escape the earth. But if it's not, then that object is going to come back to earth. So with a free fall, because we're ignoring the effect of air resistance. Okay, so the question says, which of the following combinations below regarding the magnitudes, take note of that, of the stone's velocity and acceleration at a time t1 is correct. So at time t1 we're looking the acceleration and the velocity here, and take note that we're looking for the magnitude, meaning that we don't care about the direction of whether it's going up or down. We just look in the magnitude of a velocity and acceleration at this point, right? So here we know that the slope here, even if a person is not doing maths, it's not doing physics, it's a mathematician. Also mathematicians knows that the slope at a turning point is 0. So we don't have any slope here at a turning point, meaning that the velocity at that point is 0, but the acceleration is not 0, because acceleration is given by the second derivative of this function. So here acceleration is always pointing downwards, so n is 9.8 on Earth. So this A says that velocity is 0. We agree with this one, we agree with this one, we don't agree with the last two. So want to check between the first two ones which one is correct. So B says that the acceleration at that point is 0, so that's not true. Acceleration is always 9.8 pointing downwards, but here they don't care about the direction. They're asking for a magnitude, so the correct answer here is A. So let's mark that. Okay, so let's move on to the next questions. 1.4, it says that the trolley of mass m was moving at a constant velocity v to the right on the frictionless horizontal surface. A ball of clay, also of mass m, dropped vertically, falls onto the trolley at a time t, as shown in the diagram below. Alright, so let's get the diagram. The diagram is here. The ball of clay is here, coming downwards, and here you have a trolley that's moving with a constant velocity v. Okay, so here, before you can solve the problem, you must be able to classify the problem where this is under. Is this under Newton's law? They want me to apply here Coulomb's law. They want me here to apply what is this, work energy theorem, or this is a momentum problem. So here this is a momentum problem. Okay, and it says that the ball of clay sticks to the trolley. So when this ball hits the trolley, it sticks there. Okay, so which one of the following velocity of the velocity time graph below correctly represent the velocity of the trolley before and after t? So before and after t. Okay, so let's move on. So let's first consider the conservation of linear momentum. So if you want to consider the conservation of linear momentum, you have to choose the system. So you can choose your system as a surface, trolley, and a ball. But for me to make this simple, I chose my system as a surface and a trolley. So you see how that's it's simplifying the problem. So to simplify this problem, I chose my system as this blue line here is a boundary for the system. So my system is a surface and also the trolley. Okay, so meaning that the momentum in this system must be the same always. The momentum of the system will never change. Okay, so here we have a p initial, which is a mass multiplied by velocity initial of this, and we're given the velocity initial, that's v. So p initial was mv because you have m here, but after that the trolley now has 2m, so we want to calculate the velocity final. All right, so p final is going to be the 2mv squared, or mv final. All right, so 2 is 2 because we add another m here, so it's like m plus m. Finally we're going to have 2m, and the velocity final, we don't know what's that. But I said something about the conservation of momentum. The momentum in the system must remain the same. So if we add another mass, we don't care about that, but this momentum here initial is going to be the same as the momentum final. So we have this p initial here being equal to the p final. It's a conservation of a linear momentum. So v final is going to be half v. The reason I'm saying that is because if you can take this p initial here, which is this one here, is mv, and substitute here, and take this p final, which is this here, 2v final, and then find v final, you are going to get this. So I jumped that step because this guys is a multiple choice, is 2 marks, and then if you're spending a lot of time in there, actually you are not going to finish. All right, so let's move on. So meaning that the correct answer here is C, because it was v, and then after that it moved on to half v. Okay, and that's what they ask you. They said here which of the following velocity time graph correctly represent the velocity of the trolley before and after t. So they're asking you about the velocity of the trolley only. So that C is correct. So we're going to move on to 1.5. So 1.5 says that a person lifts a crate vertically upwards at a constant velocity through a distance h. The person does a work x on the crate in the time t. Okay, so the person now lifts the same crate vertically upwards at a constant velocity through the same distance but in time 2t. Okay, so here this is a work problem, and then they're saying that the work done by the person on the crate will now be, okay, so it's like you're lifting. Let's visualize that. Let's just go to the diagram and try to see something. Okay, so you are here and then you are lifting this object from the ground to this point at distance h with a constant velocity, and you took time t, and then now we want to check what's going to be the work needed, because first the work needed for you to take this object of mass m from the ground to this point was m. So now we want to check how much work is required for you to lift this object from the ground to the same position but with the time 2t. So this guys is like, if you 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 call someone here, or someone who's I can say who has like more power than this guy to lift this thing. In order to lift this object from the ground to here, energy is it's going to be needed, and the same, this object is going to have the same energy needed to be lifted from the ground to this point, regardless of how long you take to lift the object or who's lifting the object. So in a physics way, is because we have a work, which work is the same as energy, is given by f times change of x cos theta. And again, we know that the work done, it's the same as it's measured in joules. So the work from here to there is just going to be the energy needed from here to there. So we can just say here the work is equal to the potential energy. So regardless of who's lifting this thing or how long it takes you to lift this thing, the work is not going to change, because we need the same work to lift the object from here to there. Even if you call another person, if they don't have the minimum work required to pull this object from here to there, no matter how fast they can lift it, this object is not gonna move. So it just need x. So x is the work that can move it, or amount that's a work that is greater than x can move it. Okay, so here that means the work is not going to change from here. Work is f changing x cos of theta, and since the cos theta is 1 here, so for an example of that, I can show you if object is being dropped for a certain height, from a certain height to the ground. So a work of that object, since if it's dropped, the f is going to be mass multiplied by gravity multiplied by the change of displacement, or multiplied by the displacement, sorry. So it just, that means that object, let me try to draw something, maybe you can understand it better. So I'm trying to say that you have something like this. You have something like this object. So this object is falling from a certain height, from a certain height to the ground. So this is a ground. So we know that if it's dropped, the force acting on this object is weight, and weight is given by this w, which is m multiplied by velocity. All right, so that means if you want to calculate the work, is you can calculate it by the potential energy of the object at this point, at height. So let's call this height h also, at this point. All right, so that's a great way of finding the work done. So meaning that regardless of how long this thing it will take to reach the ground, the work is going to be the same, because the work is given by potential energy, and our potential energy is going to be the same from here ground to that point. Okay, so here the correct answer here, the correct answer is going to be B. So B is going to be the correct answer. So let's circle that, B. So this is the correct answer here. Okay, yeah, B is going to be our correct answer. So this B, this is our correct answer, guys. Okay, so yeah, we're done. So in our next video, I'm just going to go through question 2. So guys, if you haven't subscribed to this YouTube channel, hit the subscribe button, please.